Well, I want to tell you about determinacy and stability of a structure. So first, what does it mean to be unstable? This would be an example of an unstable structure because it's got less than 3 reaction components. You see at A, there's a vertical reaction component, and at B, there's a vertical reaction component. What if I give this a push? If I push this horizontally, nothing is restraining it. So we would say this is an unstable structure. It's got less than 3 reaction components. It's got nothing holding it in the horizontal direction. So this would be a stable structure. It's also statically determinate. A structure is statically determinate externally if the number of reaction components equals the number of available equations, meaning 3. So I have 3 equilibrium equations here, and they're all satisfied. The sum of the forces in the x direction is 0. Sum of the forces in the y direction is 0. Sum of the moments about any point on the structure O is equal to 0. Those are all satisfied. So this is stable, and it's also statically determinate. So this is an example of a beam that is statically indeterminate externally. It's statically indeterminate if the number of reaction components is more than 3. It looks stable. It doesn't look as though it's going to move, but it looks like I have 4 reaction components. 4 reaction components, which is more than the 3 equilibrium equations that I have at my disposal. The degree of indeterminacy is equal to the number of reaction components minus 3. I say I is equal to r minus 3. Now if you have a hinge, internal hinge or an internal roller, you're releasing some internal restraints. C would be the number of internal restraints that you're releasing, and the new formula for degree of indeterminacy would be I is r minus 3 minus C. C is equal to 1 for an internal hinge, because for an internal hinge you're actually releasing an internal moment. And C would be 2 if you have an internal roller, because for an internal roller you're not only releasing moment, but you're releasing either a restraint that's horizontal or a restraint that's vertical. So the degree of indeterminacy would be different depending on how many internal releases you have. Let's say we have this simply supported beam here. To make a cut, AA, okay, after I cut it, I've got 2 halves, the left half and the right half. Maybe you remember from statics that if you cut through a beam like this, you'll have 3 internal reactions at the cut. So if we just consider the left side, I've got a shear V, I've got an internal axial force N, and an internal moment M. If I were to consider the right side, I'd have the same forces, equal in magnitude but opposite in direction. Okay, so here I am cutting through a solid portion of the beam. At the cut, I've got 3 internal reactions: shear, normal force, and moment, internal moment. Now let's just say that we've got a simply supported beam, and this one has a hinge at what I'm calling point C. So now I'm going to take a cut through that hinge, which is equivalent to saying that I'm disconnecting it at that hinge, and I'm going to consider the left side and the right side separately. Okay, so I'm cutting it at the hinge. So what do I have? Okay, well, at the hinge at point C, notice that I'm just showing a horizontal force, F sub x. I'm showing a vertical force, F sub y. I'm a little sloppy with my notation here. I could call this C sub x and C sub y if I wanted, so just please don't mind my sloppy notation. Okay, and then of course on the right portion of the beam, equal in magnitude but opposite in direction. But what is the difference between this and the previous illustration? Well, there's no internal moment, is there? No internal moment if I cut it at the hinge. So see what I'm saying at the bottom? No moment reaction, no internal moment reaction at the hinge. So that means that one internal restraint has been released. I don't have a moment there. So that would be the second scenario that I want to show. Okay, and here's the third scenario. What if I have an internal roller? Okay, take a look at what's happening at point C. I disassemble it at point C, cut AA, and then if I move this up, I've got the 2 halves of the beam, the left half and the right half. Okay, what do I see going on at point C where I made the cut? I see only a vertical reaction, and for the right side, F sub y, I could call it C sub y if I wanted, equal in magnitude but opposite in direction. So what's missing here versus the previous scenario? I don't have a horizontal force, do I? Because of the internal roller. I just have a vertical force at C. So for an internal roller, there's no moment. Okay, no moment, no internal moment. But in addition to that, there's no horizontal reaction at the roller, so I'm actually releasing two internal restraints. So how does that look? So is this determinate or indeterminate? And if it's indeterminate, what is the degree of indeterminacy? How many hinges do I have? Two hinges. See the two hinges? So each of those hinges offers one internal release. So I say two hinges, therefore C is equal to 1 each for a total of 2. So C will be 2. 1 plus 1 is 2. Okay, so what does that mean? What is the degree of indeterminacy? So what is R? R is the number of reactions. 1, 2, 3, 4, 5. So R is 5. R is 5. Okay, so indeterminacy. 5 minus 3 minus 2 is 0. Okay, so this is actually not indeterminate. It's a determinate beam. If I were to apply a load to this, I'd be able to determine the reactions. So this would be considered determinate. What if I only had one hinge? What if I only had one? Here, can I cover up one of the hinges? Okay. So pretend that the beam is continuous through point D. If I only had one hinge, then C would be 1. So I'd have 5 minus 3 minus 1. So 5 minus 3 minus 1 would be 1, meaning that it would be 1 degree of indeterminacy. But that's not the case here. I've got 2 degrees of, pardon me, I've got 0 degrees of indeterminacy. So what about this? Is this determinate or indeterminate? I've got a pin at B, and I've got a roller at A. Determinate or indeterminate? Well, what are the reactions? Well, one reaction at A, two reactions at B. So I have 3 equilibrium equations, so is this determinate? Imagine putting a load on this. So let me throw a load on here. Or F, I'll call it. What's going to happen here? Now this roller at A, that's not going to support this vertically. So if I apply a load to this F, I notice that the sum of the moments about point B will not be 0, will it? And so I have 3 reactions. However, the sum of the moments about point B will not be 0. Therefore, this is unstable. Okay, I've got something that's geometrically unstable. Very poor design. This is called a gambrel roof. So imagine that these are the 2 walls of the building. And this is the roof, an outline of the roof. So this would be part of the roof. This would be in the shape of a gambrel roof. That is, that it's got 2 different slopes on each side of the ridgeline. What if there's a hinge at the ridgeline? Is this determinate or indeterminate? So let's call this point A, and this will be point B. At A, I've got 2 reactions, and point B, I've got 1 reaction because I've got a roller there. So what is R in this case? Number of external reactions, 3. What would C be equal to? How many internal releases? There's a hinge at the ridge line, so C is 1. Okay, so is this determinate or indeterminate? Okay, what is 3 plus C? That would be 4 in this case, wouldn't it be? Okay, now in this case, R is less than 3 plus C. Because I've got 3 is less than 4. So what does that mean? If I wind up with R less than 3 plus C, that means it's unstable. So an unstable gambrel roof. Does that make sense intuitively? If you put a load on this, what's going to happen? Well, it looks like it's going to collapse at the hinge, and B will go moving off to the left or right, won't it? If I put a load on here, for example, B would move off to the right. So this is unstable. Intuitively, I can see that as well. So consider this structure: fixed at A, roller at E, internal roller at C. What's the degree of indeterminacy? Okay, so it's got 4 reactions. 4 reactions, 3 reactions at A and 1 at E. So R is 4. C is 2. Why is it 2? For an internal roller, you've got 2 internal restraints that are released. You're releasing, in this case, in the x direction, you're releasing this in the x direction, and you're also releasing an internal moment at point C. So that's why C in this case is 2, and then 3 plus C is 5. In this case, R is less than 3 plus C, meaning that this is an unstable structure.